Hello everyone, this is Stoichiometry Made Simple with Ms. Rodriguez, and today we're going over everything you need to know about the Stoichiometry Unit in high school chemistry. So today we're going over mole ratios, mole-to-mole stoichiometry, limiting reactants, percent yield, gram-to-mole stoichiometry, and gram-to-gram stoichiometry. So starting with the steps for stoichiometry. The first step is to balance your chemical equation. So if you don't already have a balanced equation, make sure you balance it beforehand. Step 2 is to find out what you know and what you want from the question. Step 3 is to set up your dimensional analysis so that your units cancel and you're left with the units you want. And step 4 is to multiply all your top numbers, multiply all your bottom numbers, and divide the two. So starting with mole ratios. Mole ratios just mean that we're using the coefficients in our balanced equation to figure out how many of compound A we need to balance out compound B. So for example, with these coefficients, we need 1 mole of compound A for every 2 moles of compound B. We need 1 mole of compound A for every 3 moles of compound C, and 1 mole of compound A for every 4 moles of compound D. For example, we have this balanced equation here, and we want to know the mole ratios of the following. So comparing C2H4 to O2, for every 1 C2H4, there are 3 O2s. So the mole ratio is 1 to 3. For every 1 C2H4, there are 2 CO2s. So that mole ratio would be 1 to 2. If we're comparing O2s to CO2, for every 3 O2s, there are 2 CO2s. So it's a 3 to 2 mole ratio. So mole ratios are all about those coefficients and the relationships with each other in a balanced equation. When we're trying to do mole-to-mole stoichiometry, we always start with our problem. So what do we know and what do we want? For this problem, we know that we have 0.83 moles of H2O. We want how many moles of O2. We have a balanced equation, so all we have to do is plug it into our dimensional analysis. We start with our know, so start with the 0.83 moles of H2O. If you have moles of H2O on top, you want moles of H2O next to the bottom. How many moles of H2O? We look at our coefficient. Our coefficient is 2, so 2 moles of H2O for every 3 moles of O2, because that's the mole ratio of H2O to O2. Moles of O2 is what we were looking for, so we can stop. We multiply our top numbers, divide by our bottom numbers. So 0.83 times 3 divided by 2 gives us our answer, which is 1.245 moles of O2. And that's how you do mole-to-mole stoichiometry. Now that we know how to do mole-to-mole stoichiometry, we can figure out the limiting and excess reactants. The limiting reactant is the reactant that is used up and limits the amount of product that can be made. The excess reactant is the reactant that is left over at the end of a reaction. So for example, if we're trying to make s'mores and we go to the grocery store, a box of graham crackers is going to have 26 squares. A bag of marshmallows is going to have 40 pieces of marshmallow, and a Hershey's pack is going to have 36 rows of chocolate. So from this equation, what is the limiting reactant? Which one runs out first? The answer is our crackers. We're going to run out of those 26 squares way before we run out of marshmallows or chocolate. So it limits the amount of s'mores that can be made. That's what makes it the limiting reactant. In this example, we have 1.2 moles of H2 and 4.7 moles of O2. How many moles of H2O can be produced? So again, we have a balanced equation. 2H2 plus 1O2 makes 2H2O. In this problem, since we have 2 knows or 2 starting numbers, we have to set up 2-dimensional analysis. So starting with our first number, we have 1.2 moles of H2. If we have H2 on top, we want H2 at the bottom. The coefficient for H2 is 2, so 2 moles of H2. And the mole ratio is 2 H2Os. So 2 moles of H2 for every 2 moles of H2O. For the O2, so now we have our other no, which is the 4.7 moles of O2. If we have O2 on top, we want O2 at the bottom. And there is 1 mole of O2 for every 2 moles of H2O. Now that we have our dimensional analysis, we multiply and divide our numbers. So 1.2 times 2 divided by 2 is able to produce 1.2 moles of H2O. 4.7 times 2 divided by 1 is able to produce 9.4 moles of H2O. So the limiting reactant would be H2. It limits the amount of H2O that can be made. Using multimole stoichiometry, we can also calculate the percent yield. Percent yield is a formula, and the formula is percent yield equals actual yield over theoretical yield times 100. The actual yield is the amount of product that is actually produced during a reaction, so like during an experiment. The theoretical yield is the amount of product a reaction should produce according to the stoichiometry conversion. So theoretical yield is like if we were in a perfect world. The actual yield is with error. So with error, how much of the product did we actually produce? For our example, again, we have two numbers, but notice this time we have a number for the reactant and a number for the product. So 0.55 moles of O2, which is a reactant, and 0.82 moles of H2O, which is the product. We have the same balanced equation, so 2H2 plus O2 makes 2H2O. We always start with what we know, so we know that we have 0.55 moles of O2, and we want to figure out, using stoichiometry, how much H2O should that be able to make. If we have O2 on top, we want O2 next at the bottom. For every 1 O2, there are 2 H2Os, so 2 moles of H2O. Once we multiply and divide our numbers, so 0.55 times 2 divided by 1 gives us a theoretical yield of 1.1 moles of H2O. So in a perfect world, theoretically, 0.55 moles of O2 should produce 1.1 moles of H2O. But that's not the case, right? In the reaction, only 0.82 moles of H2O are produced. So that means we have to find our percent yield. Actual over theoretical. Our actual was given to us, 0.82 moles of H2O. Our theoretical we calculated, so 1.1 moles of H2O. Divide your numbers, multiply by 100, and we get our percent yield, which is 74.55%. Now, everything we just did for moles to moles, you can also do for grams to moles and grams to grams. So this is how we deal with a gram to mole stoichiometry problem. So for this problem, let's identify our know and our want. We know we have 13.5 grams of Al, and we want the moles of CuSO4. Our equation is already balanced, so we're good to start our dimensional analysis. We always start with what we know, so we know we have 13.5 grams of Al. We have to turn our grams into moles first before we can use the mole ratio. We know that the relationship between moles and grams is 1 mole equals the molar mass in grams. If we have grams of Al on top, we want grams of Al at the bottom. The molar mass is your grams, so this is the molar mass of Al, which is 26.982. In this case, we found that from the periodic table since Al is an element. And the molar mass is equal to 1 mole, so 1 mole of Al. If we have moles of Al on top, we want moles of Al next at the bottom. How many moles of Al? In this equation, there are 2 of them for every 3 CuSO4s. So 2 to 3 is our mole ratio. Since this is what we were looking for, right? We wanted the moles of CuSO4. Now we just have to plug it into our calculator and figure out our answer. So multiply your top numbers, divide by your bottom numbers, 13.5 times 1 times 3, divided by 26.982 divided by 2, gives us our answer, which is 0.75 moles of CuSO4. And again, we can even take it one step further and go from gram to gram. For this problem, again, we identify our know and our want. We know we have 1.9 grams of Ca. We want the grams of AlCl3. Our equation is already balanced, so we can plug it into our dimensional analysis, starting with what we know. So starting with 1.9 grams of Ca, if we have grams of Ca on top, we want the molar mass of Ca next at the bottom, which is 40.078, which is from the periodic table since Ca is an element. And molar mass is equal to 1 mole, so 1 mole of Ca. For every 3 moles of Ca, so 3 Cas, there are 2 AlCl3s, so 3 to 2 mole ratio. But moles of AlCl3 is not what we want. We want grams. So we have to convert our moles back to grams. If we have moles of AlCl3 on top, we want moles of AlCl3 at the bottom. And to turn it into grams, we have to use that relationship, 1 mole equals molar mass again. So 1 mole of AlCl3 is equal to the molar mass of AlCl3. And if you don't know how to calculate molar mass, I do cover it in one of my previous videos. So look at the mole made simple video and I explain molar mass there. So 1 mole equals the molar mass of AlCl3 in grams, which is what we're looking for so we can stop. Multiply all your top numbers, divide by your bottom numbers. So 1.9 times 1 times 2 times 133.34 divided by 40.078 divided by 3 divided by 1, and we get our final answer, which is 4.2 grams of AlCl3. Now, for those of you taking more advanced courses that require conversions from moles to liters or moles to Avogadro's number, you can use this exact same format. Just make sure that you use the correct relationships. So instead of using 1 mole equals molar mass, you would be using 1 mole equals 6.02 times 10 to the 23 particles, or 1 mole equals 22.4 liters. So just be aware that this is the same format for those conversions. You would just use a different relationship, so a different conversion factor, but the process is the same. All right, that is everything you need to know about stoichiometry for high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If you found this video helpful, make sure you click that like button and subscribe so you don't miss any of my future chemistry content. I will be making videos soon with more stoichiometry example problems. If you're a teacher and you would like access to this exact PowerPoint, it is on my TPT store called Chemistry Made Simple, as well as worksheets, labs, and activities for this unit, as well as all other units of high school chemistry. I hope you have a great day. Bye.